All the way to talk.
Yes, we're getting little lights.
Go. It's the download. It's all set. And then connect to it.
Who does not hear this?
The other one was just a start.
Everything you see here is all of the
Less here, more.
This particular hardware version also provides up to the SVFIG. Switch on. Here. Switch on. Dishes. Yeah. Where's the 42? Send it out to the SVFIGs.
Oh, that's great. I've never.
So now I'll create a new link. Yeah. So some other demos here is Easter calculation demo. The available word for example, new word dot Easter, which when the date of Easter is 2016. So this board is hooked up to the new one. It's got the LEDs hooked up. It also has the pin header here connected. Plug a probe in onto that header. So then the pin header is on port number 2. So I want a 0 2. And then write a 1
Towards the end, and I said, here's some comments. But they actually posted that, so that might have just a little bit.
That's the square wave, 1 megahertz. So there's a 12, the CPU is running on a 12 megahertz clock. It takes 12 cycles to keep up with so you get 1 megahertz. That's a square wave. Open source software stack, running on an open source CPU, built using open source tools for the first time on FPGA and so on.
Okay.
Right. It's short. I can give you a name, because the first part,
Oh,
I think he's going to tell us all about it,
you get the live version now.
and the link will be published.
Yes. In fact, I'll send out the link afterwards. Oh, let me send out the link now. Okay.
That'll be back.
All right. So I sent out all the slides and the links. Hopefully they'll reach you in a moment. Okay, so I'm going to be talking more generally about swap forth, which is what was running on that 16-bit machine in the video from a couple of weeks ago. And before I start, I should do my usual explain what the slides are running on, because it's not just the same old PowerPoint. Slides are running on this, which is a FPGA from a company called Gadget Factory. This is their Papilio Duo board, which is a Xilinx LX9 FPGA running, and it's here running a J1B, which is the 32-bit version of the J1 at 150 megahertz. So it's pretty powerful. It's got an SD card on it, and there's a frame buffer on this. There's an external RAM on this FPGA board. It's got enough to run a giant 640 by 480 frame buffer, and that's what you're looking at right now. And there's some forth running on the soft CPU here to pull the slides off the SD card and put them onto the display. That's the board. There's the SD card up at the top and the VGA connector. The frame buffer chip, the RAM chip, is underneath. So this is a 1 megabyte frame buffer, which is why the transition takes a moment. There's a little bit of a hack going on because the actual the VGA connector is 4-bit. So if you look at that image, you can sort of see all of the banding effects, as there's actually not very many. So here's an easy hack, is just to add random number every cycle onto the pixel value, and that gives this effect. So the banding is gone, but there's a little bit of noise. If you're close to the screen there, you can see the noise, and that's it. It's just dither in its simplest form, just a stream of random numbers. Yeah, but with skin tones, of course, they don't cover the whole gamut. So with skin tones, you might only get 5 or 6 shades. So this is why it looks so awful. It's just, there's a little bit of grain in the image there, but that's caused by the random numbers. Okay, how did the slides get made? Well, they're super simple. So I take the 640, 480 PDFs. I use ImageMagick to turn them into RGBs, and then I just dump them directly onto the SD card. The SD card is just a list of 640, 480 images. There's not even a file system on it. So it works great. And now for the presentation proper. Yeah, it works great apart from that noise there, but there you go. So swap forth started off as a forth for the FT900, which is a forthcoming 32-bit chip. It's not quite out yet, but in the meantime, I've got swap forth running on various other targets. First one I did was swap forth running on 32-bit J1, the J1B, which is the sort of fancy, great big J1 with a whole 32K of RAM. And that's what I have running here on the desk. But a couple of months back, I started looking at getting it running, a tiny version running on 16-bit CPUs. And that's what I was showing in the video there, was a much reduced version. Okay, so swap forth is an open source project. You can get it on GitHub. It's BSD licensed. Everything I'm showing here today is all in that tree. And if I had to think of one word to come up to describe swap forth, it's just to be useful. It's not really an experiment in forth. It's just a standard forth. There's no innovation going on. I just needed one to do my stuff, and I do use swap forth a lot at work, and I'll be talking a bit about how it comes in handy. It's not an exercise in minimalism. It's got a whole bunch of things built into it to make it useful. And the other thing I'll be talking about today is emphasis on testing, because it's not actually very useful if I get it out of the drawer and it doesn't work. So there's a lot of testing that goes on with swap forth to keep it all functional despite the multiple targets. And those targets, so the first thing I did with swap-forth when I was extending it from its original version for the FT900 was make a Python target, which is kind of a weird choice. I mean, there are not that many forths that run on Python. But the great thing about it is that Python runs everywhere. It's super stable. And with a nucleus built in Python and the rest of swap-forth compiling on top of that, it's very easy to regress it. And Python has a bunch of things which make life super simple, like it has dictionaries, which is useful for modeling the fourth dictionary. And its arithmetic is automatically extending, so you don't have any problem with 32-bit, 64-bit, 128-bit. It all just comes with Python. So we end up with a fourth, which on the command line, you can switch between being 64, 32, and 64-bit, which is handy for testing. Also on the command line, you get big endian and little endian switching, which is actually not that interesting anymore now that there's no big endian machines left. Performance is kind of okay running on a desktop or a laptop, but performance isn't really that crucial because it's just for testing. It's just to take the fourth system and build it all of these different ways and then run on top of that the ANS test suite, which is a giant, I don't know if you've seen, Jerry Jackson is maintaining it now, is a huge set of tests for ANS fourth. So here's the actual model. There's a Python nucleus, which is obviously pure Python, and that implements a base system, just enough to be able to compile and execute words. So there's obviously the set of primitives. So it's not like eForth, for example, which I think has quite a small nucleus of about 31, 35 words. So I think it's 120. So there's a whole bunch of things it has to do before it can actually compile the rest of the system. But what does happen after that is that all of the common stuff, that magnificent representation on the right-hand side, that's the fourth source code which builds the rest of the system. So once you've got those 120 words, then the rest of swap-forth gets pulled in as include files. And that's what's shared between all the targets. What's it useful for? Well, it's in GitHub, the whole project, and Travis gives you free continuous integration. So they will, at no charge to you, every time you make a check-in, pull your tree into a freshly booted virtual machine, build it, run whatever tests you like, and then send you an email if the test failed. All for the low, low price of nothing. And if you look down at the bottom there, that green badge means that the Travis build passed with the last check-in. So every time something changes, within about a minute, if I've broken it, at least at the fourth level, say I broke something for 16-bit big endian fourth, I'll get an email saying, fix it. Okay, so the next target I'll show is the one I was showing in the video, which is the J1A. J1A is the original J1 that I made about 5 years ago, but stripped down. There's a few things that I changed for the J1A. The ALU is a bit simplified. The old ALU had like multi-bit shifts, which on most FPGAs, it builds a barrel shifter, and that sucks. That was like half the ALU. So removing it shrunk it by half. And the other thing that is fixed is that the RAM system for the old Xilinx model, Xilinx and Altera have dual-ported RAMs. So you can kind of see there that there's two RAM fetches going on there on the left. There's the instruction fetch and the data fetch. And that's fine if you've got dual-ported RAMs, but what was interesting this year was lattice FPGAs, very low-end, ultra-low-power lattice FPGAs. They don't have dual-ported RAM, so I had to get it to work with single-ported RAM, pseudo-dual-ported. It has a single read port and a single write port, so you've kind of got this classic von Neumann bottleneck now. You can only fetch one word per clock, including the instruction word, which J1 is a single cycle CPU, so it's not going to be running multi-cycle operations while it fetches an instruction and then fetches data. So that had to be worked around. So what J1A is much reduced and simpler RAM model to fit onto this quite tiny FPGA, which they sell it as an FPGA, but by some reckonings it's just a CPLD, just this sort of tiny amount of logic and not very generous RAM either. So the whole thing fits on that. It uses up almost all of the logic because of things like the UART and the I/O. I mean, it doesn't seem much point in leaving over unused logic, but there is plenty of RAM left over. The whole thing only takes 4.5K of RAM, leaving a whole 3.5K for your application. So plenty of room. Yeah. So that's what there's a manual that comes with it, so it's all ready to use. You just download it onto the FPGA, and a few people have done it. It seems to be working for them. And then you connect to the UART, and that's what you get. You get the full set of the ANS core, so it can actually run the ANS core tests. And then there's a few odds and ends. These are really just factors which got used as part of the core system to build the compiler, so you get those for free. And this is what's built into that 4.5K of code. This is your base system. So it does everything you'd expect from a minimal 16-bit fourth system. No surprises at all. Some bits of fourth 2000X are kind of long, like dealing with the number prefixes. That's annoying and time consuming, but of course a lot of fourth code now does just say $ for hex numbers. You kind of got to have it. Rest of it, there's an interesting aspect of doing an ANS fourth is that whether a word is immediate or not is only actually comes up in one word. If you it's the word find. So immediacy is all encapsulated in that one word. So you can use all sorts of ways of encoding immediacy, and provided nobody looks under the covers to see how you're actually representing your dictionary or immediacy, you can put everything inside there. So for example, the Python version of find just looks it up in a dictionary. And this version of find uses a couple of other tricks to squeeze memory down. So all the different targets use a different way of representing the dictionary. Obviously, the dictionary is super important for performance, for compilation performance. So dictionary, it's not one of those fourths where every swap fourth you could look underneath and examine the dictionary and write portable code between the swap fourths. They're all different once you go past the ANS layer. Oh, what can you do with it? Where can you run it? This is Verilator project, another open source project. What you do is you take your Verilog, compile it with Verilator, and what it spits out is C++ code which runs the simulation of your Verilog. So instead of running your Verilog through a emulator or simulator like Icarus is a very well-known open source simulator, which is quite slow, Verilator just produces this super fast C++ code which runs your simulated CPU. And if you can see that, that's the CPU running. That's a wave of a CPU executing instructions, and that's what you actually get when you simulate it. If you look down at the wave level, but Verilator, because it outputs C++, you don't actually just have to run the C++ application. You can take your original Verilog, Verilator turns it into C++. You provide a small stub to interface that C++ to Python, so it starts to look like the whole thing on the right-hand side starts to look like a Python module. And with that module, you can interface it to Python running on the host. And the shell that I'm using on the host, sometimes I use the terminal to talk to swapforth, but normally I use a Python shell which talks on the UART. Those lines there are just the UART protocol. So there's a UART read and a UART write call, read and write. And that's what that thing is pretending to be. It's pretending to be a UART. So as far as this shell is concerned, it's talking to a UART up and down those links. But what it's really doing is talking to the simulator. So what the shell is polymorphic. It either talks on the UART or it talks on this simulated UART interface. And the upshot is that you get this. You get a thing running on your system which looks like a live fourth machine, but really you're running a real-time C++ simulator of the RTL. There's no hardware involved. And this is a big help for testing because it's a big pain if you can only run your tests on a machine with the damn hardware plugged into a USB that you have to unplug and plug in to get to start up. This just runs entirely in simulation, so it runs anyway, it runs on the cloud. And this is one of the things that Travis builds, is this simulator builds the fourth, runs the fourth compiles the rest of swap fourth, and then runs all of the ANS tests, and then produces this completion report. And this all happens in about 4 seconds from an empty machine. And the great thing about Verilator is it's super fast. So the simulation rate, which on Icarus is much slower than the physical hardware, is actually faster on a desktop machine anyway than the physical hardware. So the FPGA runs at 12 megahertz. This thing runs, depending on how hard your instructions are, runs at about 30 megahertz. So it's quicker than the hardware. Okay, so that also gets run every step. So every check-in, it's rebuilding the simulator, running it, the simulated J1A, and gets verified by that Travis build step. Well, of course, it's actually not just to be simulated and tested. There's an actual hardware target here, and that is this chip from Lattice. Lattice bought a company called Silicon Blue, a startup a few years ago, who were trying to introduce super low-end FPGAs. So these are FPGAs with not many gates, not much RAM, but are cheap and low power. And believe it or not, I think the package there is their evaluation version. I don't think anybody in production would use this giant package. But you can get them in tiny 16-pin BGAs, this FPGA model. So I think they're 1.2 millimeter square. So they are very small FPGAs. But this is what they make. This is a $22 board with, obviously it plugs straight into USB to save on the connector there. It's got a dual port FTDI chip. It's got quite a 2 megabyte flash. There's the FPGA, and then on the right-hand side is an infrared port, and then just a bunch of GPIOs and some LEDs, and that's what I was showing in the demo. So you get quite a lot for your $22. But the bad part of it is you have to use the Lattice toolchain, which is license locked, and everybody who uses it said they spent a day trying to get it set up. It's awful, and don't bother calling Lattice about it because they're not on your side. I don't know why all the vendors' FPGA tools suck. I think it's probably because they don't want to annoy Synopsys, who sell commercial FPGA compilers. So if you're in competition with Synopsys, who's also your partner, maybe contractually you have to make sucky tools with awful node lock licenses. I mean, there's something going on. So some people got sick of this a few months back, and because the Silicon Blue architecture is actually quite straightforward, and because startups tend to be a little bit less opaque about their designs, their datasheet tells you quite a lot about the chip, and you can look inside the configuration file, reverse engineer it, which is probably violating something, and understand how it works. It's not that complicated. And that's what they've done. There's now an open source tool chain for Lattice for these particular chips, which is a big deal because the last time there was an open source tool chain for some low-end Xilinx chips was like 15 years ago before Xilinx shut that project down. So for now, this thing exists, and we'll see how that goes. But as soon as I saw this project, I wondered if maybe it could compile a CPU because all it could do was flash LEDs at the point where I was looking at it in March. And it seemed like a pretty awesome thing to try to fit a J1 into it and run the first ever open source CPU running on open source FPGA tools. And with a bit of squeezing, this is why the J1A got reduced that way, it does actually kind of fit. It's like 90% of the available gates are taken up, but it does fit. And then, what is it actually useful for? It's pretty awesome that you can get an open source CPU on a stick, but is it actually useful for anything apart from obviously computing the date of Easter? Well, this is something that I've used. I'd be interested if anybody else has used anything else in this family. What it is, it's a lab jack, and you plug it in. That's a USB connector on the end. And what it gives you is some GPIOs that you control through USB on your PC. And I use them at work because this is how we would control motors and things. I'll continue. This is another variation. This is an FTDI MP SSE cable, which once again is a USB device. You've got some APIs on your PC, and then it gives you some GPIOs that you can plug into your circuit. And it does a few protocols like I2C and SPI, JTAG. Those are built into the hardware. There's a chip in the plug there that's doing those protocols. That's I think these are $26. The other one is $100. See where I'm headed with this. This is Bus Pirate. If you've seen this, this is made by Dangerous Prototypes. This also plugs into your USB. Once again, it speaks some protocols. There's a PIC in there that runs a sort of command interpreter. It's got a command line this time, and you can flip GPIOs, but also run I2C and SPI. I used to have one, but each time you use it, you have to flash it to load the latest protocols into it. Some protocols don't fit in the available space, so you're continuously re-flashing it until I eventually made a mistake and bricked mine. But once again, this is a $25 thing to do the same stuff. All of these things are the same job. They take USB and work pins and to some extent speak some protocol, which may or may not match what you want. Well, this looks pretty good. It's got proper FTDI USB, and it can speak at 0.5 megabit down just over a serial connection. It's got plenty of GPIOs, nice fast ones. But best of all, it's programmable. So you can log into it and mess around with GPIOs, but when you've got some protocol like SPI or JTAG or whatever it is, you can just send some forth down that you've been incrementally developing, and there you go. You've got this thing which you can, for example, load JTAG. You can give it 1K of JTAG and have it communicate the JTAG over the pin. So you're not writing this very slow USB protocol to drive the pins. So that's what I've been using it for. So it's a great way of stimulating circuits, and I was using it for doing SPI work. Works great. So that's one possible application. And what's nice about it is instead of speaking the goofy APIs that each of these different devices had, you're actually just coding native forth to run the GPIOs, which to some people is just another goofy API, but at least it's one that you've got at the source level that you can actually port around the place. All right, so that was J1A. It's running great. It's in the tree. The tree has a pre-built binary, so you don't even have to get anything ready. You can just get that stick, send the binary down to it, and then it's a forth with all of those GPIOs available. So J1B is a bigger version. So J1's configurable, so you can make a 32-bit version instead. And this FPGA is enormous, so I think the J1B takes less than 10% of it. So you get a 32-bit CPU, and with a bit of tuning, I have it running at sort of 150. Depending on how lucky you feel, you can run it at 200, and it seems to still be stable. So it's pretty speedy. So you get 200 MIPS on a 32-bit CPU, and it's hooked up to all the peripherals. All the GPIOs are again hooked up, and you get this external RAM. I think this is it over here, and that's what's running the frame buffer right now. So that's this thing here. And yep, there's its statistics. So it's got a huge amount of RAM, so it can so the actual fourth with everything in it. I don't have floating point in it, but I think the fourth is about 12K. So there's another 20K for your stuff, which is quite a lot. One of the things it can run is the FT800 driver that I showed last time. So the FT800 fourth library, this is just a screenshot from it running. It's talking over SPI, so that's an SPI peripheral, and there's no SPI hardware, it's just running bit banging, but it's at 150 MIPS. You've got no problem keeping up with SPI. In fact, you have to put some NOPs in there to avoid electrical problems. So this runs great, and so do a whole bunch of other things. 32K, you do eventually run out. I'm not saying 32K is a limitless pool of memory, but for a fourth, particularly with the J1, it's quite compact. And one difference between the J1A and the J1B is the J1A is pretty stripped down, so the compiler in the J1A is dumb. But for the J1B, there's an optimizing compiler, and it does things like the tail call optimization and more inlining. So the J1B produces much more compact code. Having said that, they are both minimal CPUs. Neither of them, they're both this tiny CPU core, which doesn't have a bunch of stuff. So they don't have interrupts. They don't have subtract. There's no byte memory access. Byte memory access is a subroutine to do a word memory and do a lot of shifting and accessing. So on some operations, they're a disaster. But for a lot of stuff, they do just fine. What was I going to say? Okay. All right, and that's it for the J1A and J1B. There's another directory in the tree, which is the FT900 port, which is what I showed at last fourth day. That's still there. FT900 is going to be releasing shortly, and I'll maybe present more on that because that's a giant CPU by comparison, and that has 320K of memory, so it's enormous. So it's a dream machine. But these ones, the J1A and J1B, are the sort of minimal platforms, and they all do run from. They have different nucleus, but they all run from the same high-level fourth source code. Here is comparison. Obviously, I wasn't going to make a 16-bit version because 16-bit code is kind of a pain to work with these days. There's not that much of it around. But J1A kind of forced me into it. So you get 8K of memory on the mini one, 32K on the, and then 320K on the biggest one. And here I'm running a benchmark. Fib2 is an iterative benchmark computing Fibonacci numbers. This is not really a fair comparison because the FT900 is running at 150 megahertz. This is just absolute time. 36 milliseconds on the fast machine, 47 milliseconds on a 150 megahertz machine. And then the J1A, because the open source project doesn't let you control the PLL, is actually just running at 12 megahertz all the time. There's no way to run faster than 12 right now. Maybe they have fixed the PLL, but for now it's just locked at 12. But as a fairer comparison and to give an idea of relative energy consumption in clocks, you can see that FT900 is super efficient because it has fancy instructions like subtract, which is good for loops. J1B sort of does all right despite its lack of facilities. I mean, almost every operation you can think of on J1B is a subroutine call. This sort of add is built in. You get that. But that's at 5.8, and then J1A is full of compromises just to save space and gates, and so that's obviously much less efficient. And I think that is the end of my slides. Thank you.
So slides are being run from that little
Right.
But did the data for those slides come from the computer?
Repeat the question.
The data for the slides is actually coming from the SD card, which is right here on the.
So it's not connected to the computer at all.
No. In fact, it's running off a battery here. There's the PC is not part of the story. Yeah, so it boots up and it's got the FPGA image in Flash, so it just comes up. It's I should turn it. Oh, instant. It's fourth. So that's the other thing is there's no interrupts on the J1. So if you hang it, it's kind of annoying because you've got to switch it off and on again. So Control C at the shell actually just resets it. That's all it's got as far as. And that is, of course, instant because it just comes back into quit as soon as you press Control C, applies the reset signal, and it's back up. So the boot time is negligible. Yep. Yeah. So the question was, is the dictionary on in the RAM on the device? And yeah, it's Forth's blessing and curse that you've got the dictionary, which in a C model, for example, that's the symbol table, which is long gone by the time you're targeting the device. But on all of these Forths, the dictionary has to live on the device. I don't do any dictionary compression, so if you look at the hex dump of memory, all the words are just sitting there as ASCII. So some people, I mean, Chuck, for example, does an Huffman encoding on them, but no, in this one, they're just sitting there as ASCII, takes up a bunch of space, it's disappointing, but if you're going to compile on the device, you have to have the dictionary available.
So can it be in the SD card as a speed?
Yeah, could do. I mean, that would make it a lot slower because dictionary searches. Oh, could you put the dictionary on the SD card? So what I'm looking at now is running a device with no external storage, because that small FPGA, the one that is as a 16-pin, could actually run completely standalone with no external flash. In which case, there's no external SD card, no external memory at all, but it still might be interesting to run that with an interpreter. So yeah, you could make use of external memory to do fancier things. What I'm hoping to do on the bigger, on this guy, because the flash is enormous. It's several mega. I think it's 4 megabytes, which is a lot bigger than 8K. So I think I'm going to implement the block word set. So then it could run a lot of code as blocks, maybe even run entire applications if you're careful to interpret code rather than compile it. This is the lattice tiny FPGA. This is J1A. Right. But the flash is just, I've got the flash running. It's easy enough. It's just hooked up to an SPI interface on the board, so it's just a couple of words to access it. It's not very fancy, and so it's a small step then to implement blocks. So this thing isn't going to run a file system, not in 3K, but blocks. Right. There's nothing there, so that's a possible. Yeah, I was against blocks until I encountered a machine. Well, you have no choice. Then I think it's an excellent idea.
Could you say a few words about the lattice hardware? Is it one shot or reprogrammable if you make a mistake?
Oh yeah, so I think I haven't looked at their whole product line. Their product line is getting kind of complicated. But what they have is like all FPGAs, the configuration comes from RAM. So you send in this 32K of this, what was formerly an encrypted binary, which configures the FPGA. And that's how you normally develop on it. But these chips, because they are targeting the low end, have OTP programmable. And so you get one shot. So obviously you don't want to be burning your chips all the time. But as soon as you're in production, you'd use the OTP facility, and then you don't need anything external to boot them. So in a minimum system, the curse of FPGAs has always been the support chips and and also their enormous expense. But the silicon blue thing was very low end, actually targeting consumer applications like mobile. So you'd end up with this tiny BGA, which costs, I think the current one is $1.60. And it runs off a single supply. It's got high current. It looks like a microcontroller on the outside, and it's OTP programmable, so you can program it in production, or they'll program it for you for a small sum. So it's kind of interesting the way they've done that. But I haven't actually burned the OTP yet because that's a big a big commitment. But you could make a $1.60 fourth system if you don't include the USB connection. You can make a $1.60 standalone fourth system running on it using these open source tools, using an open source CPU. So it's now possible to make a super low end fourth computer, which is not completely useless, which I find surprising. So, okay, sure.
So I heard about this
900, yeah.
a year ago, perhaps, and apparently it's not built yet.
They are shipping evaluation boards, but it hasn't reached DigiKey yet. So as soon as it's actually out in proper production, then I'll make a real release. Right now, I'm kind of just doing occasional optimizations. But right, I mean, obviously it's not going to be $1.60, but then it's enormous by comparison. And yeah, I'm having great time with my evaluation boards, but obviously until it actually gets out there, there's not much point in doing a release.
Well, the name of the company is, after all, Future Technology.
That's right. Hopefully today. Okay, that's all I got. Thank you.
How come we can't get to the port.org website?
Because they're it's down.
The website's down.
And I talked to Skip, and it was one of these older servers, so actually move it to the ISP, to the hardware.
Nice.
So we manage it. That's how long it will take.
How long does it take? How long does it take? Oh, yeah.
He's still responding to us.
Yeah, it takes always 15 minutes.
I want you to keep up with the once a year. 4th day time. Never responded. So, sort of last year, I stopped sending out 5 once in a while. It's coming back late. I would send out the same VIP message to everyone on email. Last year I didn't write one, I didn't send one. He has some quote.
All the way.
All right, let me try that one more time. I'm Brad Nelson. I'm going to talk to you briefly about what's been up with the Fourth Haiku website and what I've been up to try to make it better. And well, let's get started. This month I've done something that I've been meaning to do for a while, which is I've tried to make it a little bit easier to just go through the month's haikus in a single slideshow without me having to actually do the work of sort of manually bucket bailing the code and the haiku into a slide presentation. So we'll give that a try, see how that goes, see if that makes it easier or worse. So we'll start with a tour of what's been going on this month and make sure that works. So well, this is actually from last month, but I've got the clicker going and I can just sort of have an URL that I can go to that gives me all of them sort of in a continuous stream. There's a little bit of a size problem in that I had to, unfortunately, it doesn't actually adapt to the size of the display. I'll get that sorted out. This is what happens when you decide you're going to do something clever at 10 o'clock at night and the night before the presentation. So anyhow, the size is baked in. I'll fix it. It's good. So, well, we've got a bunch of interesting things. So I should show you the other little feature. So I've got the extra button on the clicker, and I can toggle down to look at the source. So there we go. So finally, simple things. So this one's coming in. I don't know who Charlie is, but hello, Charlie. There's your smooth step. So this is lovely. We have a shining cross, which is from one of our Taiwanese friends, and there's lovely whatnot. And then, well, snow. This one's easy, random. So, not a problem. But random rings, so, there's learning going on, something. This one's kind of cool. I don't know if it's original or whatnot, but this is, actually, that's something I should add back in, is for those of you not here last month, I added in a mechanism to display the lineage of the haiku, but unfortunately it didn't dawn on me to put that into the slideshow. So, well, something to add. Yeah, something to add for next time. But anyways, it's sorry, Ted. Oh, really? How old? Well, okay. This is Sam Chen's granddaughter, who is 12 years old. That's we have this one. This is very lovely, and it's delightful. Yeah, it's nice. It's actually nice to be able to just kind of consult them and pop them up. That's all the source. Isn't that neat? I should say, I have a colleague at work who, we're working on this standard for WebAssembly, and one of the experiments that we're doing with that is, he's put together a sample application that lets you convert from this format that we're working on, which is sort of C-derived, to an image, much like the haiku. In fact, I showed him the haikus, and this was his inspiration. But the size of the programs to do even very simple things are shocking. Where something like so he'll have a huge program to do a spiral or something. So anyhow, it's amazing what you can do with a little bit of Fourth. This is delightful. And not much to it, really. Yes.
Everybody else already knows this code. So the dot in front of the state file there means it's a double station operation.
So the quirk of haiku Fourth is that the data and return stacks are both floating point. This was mainly done because in order to make the animation feasible, I'm running this on the GPU, and so the GPU was already biased towards floats. It's an unusual choice, but so there's implicit float in everything. the other thing to be aware of is that what you're providing is actually a kernel that's executed once per pixel, and so there are a couple of keywords like X and Y and T for time, and those are provided at each pixel, and the entire program is evaluated once per pixel. So there's sort of an, a wrapper around the whole thing. Here's this delightful color circle. Yeah, and not much. And look here, we confirmed that I've actually got the handling of Unicode characters right, because we've got comments in Chinese. Are they meaningful comments, Ting? Well, we got that bit. So, yeah. That does look like a virus. Again, a little bit of the fourth and the power of math also, to be honest. Yeah. And ooh, this one's ooh. So it's a little bit bigger and has comments too. Someone's got. Ooh. And of course, more fun with Pac-Man. Someone's decided to mess with it. There. This one's clipped at the bottom. You can see this is not the whole program. The way to tell if it's the whole program actually is if you go back, you can see the more tag there. Here, this one's clipped, unfortunately. Let's see. And more. Pac-Man eats beans. Okay. Some of the time. Oop. Beans prepared. Oh dear. Fish. Not sure why this is a fish, but okay. And so one lovely feature, again, for those unacquainted, is that the haiku site lets you click to clone an existing haiku and produce a Redux version of it. And so many of the existing haikus spawn derived works. Last month, I actually added a feature that lets you track the lineage of them. I made the mistake of actually not recording in the early days which haikus were derived from which, and so I did a retrospective recreation of the lineage of all of them based on similarity of the source code and title and such. For beating beans, let's move on to this, X Redux. So here's someone's actually put comments in their code, which is nice, maybe. But. Creation and running. This is derived from someone else, and you can see there's quite a lot of, this is clipped again, so this one's got more complexity to it. And man running on a gradient, apparently. And, oh, hey. Very nice. I'm assuming these are all quite large. But notice we're starting to get lots of comments. And then we got a spate of flags. Dr. Ting has been involved, although actually Miles is who? This is the one of the kids, or? 5 minutes, you say? Okay. So, but nice use of masks here. Right. Yeah, flag of France. Yeah, the flags are nice because they're compact, and I'm sensing a theme here. A lot of flags have this pattern. Nigeria, Peru. Yeah, yes, you've got a good question. One thing I did with this slideshow, which I didn't dawn on me until you mentioned it, is that so the haikus are normally displayed in a square, and the slideshow I wanted to fill the screen, so I continue the space outside of the normal range of the haiku, which for a haiku that's actually designed for the space of the square is a bad choice. I may revisit that actually in the future because, of course, now I'm destroying the nice symmetry of these flags by displaying them in this way. That's a good. Indeed, indeed. Yeah, it's actually kind of inconvenient for that. It's one of my long-standing France and Austria. Okay, we have another. Wow, there's a huge class of flags with a common. Oh, another version of this guy. Somebody. Oh yeah, he's been. The notice here. We're starting to acquire some Chinese words in the haiku text. I don't know what flag this is actually. Oh, you know, actually, this is another case I bet where it's getting we're getting undesirable behavior, because if you imagine a square in the center, that's the region that the haiku is really designed for. This is sort of excess off the brim. Okay, well, definitely something to revise for next time. I guess you're going to get black bars on the side. Well, this is a fun one. That's got a lot of code to it, it looks like. Virus colony. Yeah. Chessboard. Not much for chessboard.
I think on the last one,
Yeah.
there's actually lifetime to them. I think they fade out.
Yeah, I suspect, I doubt this is anything actually stateful, because you can't actually retain state. So most likely this is actually some, right, it's random with some function that's fading over time, but he's probably discretized it so that as they go through states, that's my guess, but it's hard to say. They're very cryptic.
There are several levels of brightness.
Chessboard, yeah. Waiting. Mauritius. Monaco. Nigeria.
Close enough, close enough.
Oh, wow. Oh, yeah?
I know some sculpture from Palau just down the road here. Where? There's some sculpture from Palau to Guinea just down the road here, yeah. They had these guys come and carve up trees that we brought.
Poland. Is this really the flag of Seychelles? That's wow. That's an interest. Oh, it's the square issue. Yeah, definitely got to get that fixed. Oh, here's Switzerland, of course. Too bad. Sweden, lovely. Denmark. I see you gave up filling out the name field each time. Iceland, lovely. Norway, Chad.
Flag of Germany.
Okay, and again, I assume this one's another needs the square. Ah.
This guy at work, we asked him if his heritage was from Finland. He didn't really understand. I said, "Are you Finnish?"
Ah.
He said, "No, I'm just getting started."
So here's another one where I what's that? Well, so yet again, it's my clipping issue. Yeah, not a square. Gotta stick to my. If I commit to a square standard, I've got to stick with it, I'm afraid.
We all learned about redefined X.
Well, I could stretch it, but then many of the haikus are designed for a particular aspect ratio. I'm torn here. I got to figure out what the. Programmable. There we go. Ah, so now this one's fun here. Notice we've got the wiggles, and this is something that Dr. Ting pinged me about. We've actually got. He was doing these with several sine waves actually together for lack of a triangle wave. As it turns out, the abs function is the trick to getting your triangle wave, which.
A little more bandwidth.
Quite. Sudan. So let's see. We got. I think we'll get to some of those in a moment here. Tanzania. Very good. Tonga. Oh, and yet again, the clipped in the Yemen. You really went through the. Okay, now there we go. That's a little bit bold. A little bit more complexity there. Uh-huh.
And actually, this flag is the combination of British flag and Scotland. Scottish is a cross with a text, and British is a cross. So what is the Welsh in the top? Okay. How the Welsh feel about it, you know? Is that the proper alignment of the red lines, or they don't?
No. This is yet again. This is the square being cut off. That's from the extending out off the sides. Yeah, if I had stretched, it would be actually more correct in this. Right, with these flags, right, they're typically rectangles, but because I'm instead exploring the space out of the region outside of what the haiku was intended to be drawn at.
We see the one side is the one side of it. This is and it was when they formed United Kingdom, we just take two flags and combine them together. They added it together.
Well, yet again, I've destroyed Greece here by not clipping again. So this will teach me to actually go and think through the list of haikus. But yeah, I'm definitely going to go with a square boundary. Oh yeah, so here now I've got the triangle wave using abs. What's that? Oh, show the code. Yeah. There we go. Yes. So. And that lets me do the version that doesn't have the wiggles. So, this actually bumps into something that Dr. Ting raises that I'm going to talk about. But at some point, and Ting was the first to notice this actually, I quietly, quite early in the process with the haikus, took away if else then. And thanks to his prompting, I have also added it back in with certain limitations that I'll discuss in more detail. But this version is done with, this is the one using if else then. This is without. You can do it, but it's a little bit more dancing around. Yeah. We got this twister. And the shaded twister. I guess it's shaded because, oh, I see, that's flat shaded, and this has a little bit of contour to it. Oh, we should look at the code for these. Oh, those are big. Textured twister. Shaded twister small. Oh, so that's the whole code for this one. That's pretty good. This is what happens when you use single letter words, though, for everything. I should mention again, for those without the context, some of the folks that submit most actively to the haiku site are a bunch of demo sceners, and they compete over the size of the haiku down to the number of bytes. And so for them, having all of the words be a single character is a way to make sure that they get as few bytes as possible. Some of the haikus you'll see labeled with a count of exactly how many bytes they are and whatnot. I had foolishly thought that we would focus on the number of words, but you know, apparently bytes is their metric. So fancy. Ricky, do you know who Ricky is? Ricky is just Ricky. Oh, okay. Huh. Well, pizza. And again, this one was again intended to just be the semicircle, but was clipped. Yeah, definitely got to put the black bars in for the next. Michelle, somebody modified it in some way that's not clear, and he changed the T to a 1 apparently, and he added comments of some sort. And ooh, and make it move. Which, put a little bit of T in there and you can get the world to move. And our pizza, and a little bit of, what does that say, Ting? Unclear. Oh, this is, I've got the text too small. I apologize. This one's fun. Somebody's always, this is derived from one of these loosely Mandelbrot related ones. You can kind of see the Mandelbrot set embedded in there in weird ways. It's a big one. And more of that. And this one's, Oh, actually, well, look at the code. That's a little more involved. Color balls. Kind of see the color balls. A little bit involved. And kind of blends together. And
You know, some of these are suitable for an art show.
yeah. That's tiny too, this one.
Displays, on the gallery wall.
And actually that reminds me, so I need to actually get back to this guy. He emailed me, so he's got his Mandelbrot. I think he, one unfortunate property of the site is that things that have been done before sort of drip down to the past. It's easy to spot the ones that got upvoted. It's easy to see the recent ones. It's hard to see what's come before. So he was presumably unaware that there have been previous Mandelbrots. So he went and did this version, you know, sort of very literally. But then he sent me an email. I need to still reply to him because he was upset that recursion doesn't work. And unfortunately for Haiku 4th, I don't have any looping primitives for reasons of being able to, well, anyways, I'll talk about that in a little bit. And Mandelbrot in set, okay. I'm not sure what that in set means. Oh, it's like in this, it's read in the set, okay. And some of these, and this one, a little bit of pseudo spam here. I discovered that my spam filter, while I limit that you don't have, so I was getting a bunch of spam, again, for those of you who are unfamiliar with the context, and I put in a bunch of restrictions around the submissions. I didn't want to actually require people to log in to submit a haiku. And so I put in a number of different restrictions. One of them is I was getting a particular kind of auto-generated spam where I would get these long strings of, 40-character words with random characters. And so I now silently reject your haiku if it contains words more than, that have more than 30 characters in the word. However, I failed to restrict that the total length of the title or author field is kept. And so someone seems to have pasted in either intentionally or unintentionally the text of a whole haiku. So I've since corrected that. So this will be the last piece of spam of this particular variety. And someone has revised color balls. And it's big. And that's the last of this set. So on to that's our tour. So I thought I'd talk a little bit about if, else, then, because as Dr. Ting noticed, I had taken if, else, then away, and I sent him an explanation of why, but I suspect that it ended up being more opaque than I'd intended. So I thought I'd have another go, although I confess that in my desperation for material to talk on, I cribbed some of the email text that I had sent to him for the contents of this presentation. So the reason this is challenging in the context of 4th haiku is that I'm under the covers converting 4th first to JavaScript, and then from JavaScript to a WebGL shader. And so I'm, and while the WebGL shaders are basically C, and JavaScript is actually quite flexible, I'm in particular not just trying to get a program that runs, but a program that has certain performance characteristics, because in order to be able to animate them as quickly as all of this, they need to be a kind of program that the JavaScript engine or the, in particular, the shader compiler is able to execute well. And so having something like an explicit stack completely horks the plumbing, particularly in the JavaScript engines, and to some degree would be an issue with the shaders. And so I go through a rather unusual process to compile them, and I'm going to describe what I was doing before and what it occurred to me that I could do that's a sort of an incremental step better when Ting said, what happened to my if-else then? So here's how I optimize a haiku currently. I inline everything because, again, I'm trying to execute it over and over per pixel. And so I don't want the cost of function calls. This has a number of drawbacks in terms of the complexity and the program that you get, but it lets me accomplish another goal that I had, which is that I don't want the haikus to be able to attack people using the site in the sense of overwhelming the page. And so if I've inlined everything and there's no loops, I know how many operations there are in the haiku, and so I can put a hard cap on this haiku can only spend this amount of computation per pixel. I could do that other ways by restricting how many cycles it runs, but that's not easy to do with a GPU shader. The assumption is that you've provided the GPU shader, it will run to completion. You would have to put conditionals throughout the shader to check, okay, have I exhausted my time slice or something in order to, so you'd be paying for it throughout. So this lets me do that. So I convert to JavaScript, as I said. What that really means, I initially just convert to a very dumb representation in JavaScript where I use a JavaScript array pushing values onto a stack and popping them off to decode. And then what I do is what I had been doing was I replace each pop as I encounter them with a value that comes from the nearest push. And I just sort of do this over and over, and I do this with both the data stack and the return stack until I've collapsed the program down into variables. And yeah, sorry, repeat. And so let me run through what this looks like for a small program like this. This expands into something like this at the beginning of the process. And so you're pushing X on, so X and Y are parameters coming into the haiku from the outside, so they're effectively special. So I'm pushing each of those onto the data stack, and then I'm pushing their product after popping off each one. And then for dupe, I create a temporary and then push that same value. And there's a reason for that that will be apparent as we go through this process. And then I do the dupe again where I'm popping and pushing. And then I finally pull the result of all of that out into some variable. So remember I said before what I would do is I would find the first pop and I would collapse the, so that push goes away and the value gets pulled in. And then the same thing with the next one. And then this value is going to get pulled into there. And then this value gets pulled, oops, sorry, back up. So remember there's this T, so this value is now done. So then I'm looking at this T goes into there. And then this T goes into there. And then the product goes into there. And so you get a version of this program that's been reduced to be expressed in terms of variables. And the reason, again, this is critical for JavaScript and for OpenGL shaders is that they think in terms of variables, and they think in terms of allocating that to registers. So they're not going to do good things if your data stack is a region in memory, because they assume, oh, that needs to actually be a load in a store. Whereas if you're doing variables, that it can optimize, it can do a very very performant code to be able to keep up with the frame rate that I want. The problem, though, is that with something like if-else then, this very simple approach that I was using to collapse the fourth program into variables doesn't work. If I have some pop that's over here and then I'm referencing it inside of one of the branches of the if-else, I'm going to get the wrong result if I just sort of willy-nilly grab the nearest guy. And so I had various ideas for how I could do that, but they were all sort of complicated and involved a lot more work than what I was currently doing, and time is scarce. So here's what I'm going to do to optimize wisely what I've now transitioned to doing. So at compile time, as I'm compiling the program, I keep a D stack and an R stack, and I walk the haiku in order, and I push and pop whole expressions into my D stack and R stack. Bear in mind my compile time D stack and R stack, and then when I encounter conditional, I keep a sort of a conventional conditional stack. I don't mess with it being on the D stack because I've got, this is sort of not normal forth anyhow, and I capture the entire state of the D stack and the R stack whenever I'm would in a normal forth would be stashing away just the origin or the destination values on the conditional stack. And then the key thing is that when I come back together and I'm popping off values and joining a branch, I insist that both of the branches match up, that the R stack and the D stack need to match up so that I can resolve everything down to a single variable. So this has a huge implication in terms of what you can do, because it means that both branches can't have any, they have to have the same net effect on the D stack and R stack in terms of their depth. I see people smiling in the audience, laughing, yes. So it's poor man's if, I guess you could say, kind of. I find that I have difficulty thinking of the cases where you wouldn't want those two to match, but I'm sure that everyone in this audience is going to raise their fist at me and say, this is no good. This is what I was able to do. And so then when I fold them together, I need to make all of the entries that don't match. If there's things that match, they can stay in the same variable slot, or otherwise I need to make them unique. And so running through how this works, now I'm walking down the haiku, so I'm pushing X, so I could just push X, and by X I don't mean, I mean literally the string X onto this D stack, and the same thing with Y. And then when I do a pop, I'm pulling that back into this expression, and the same thing with X. And then I push the entire thing back up into the stack, and then I can pop it back out to pull into T, push T in there, push another T in there, pop them back out into this value, pop the combination in, and then pop the whole expression out. So I get the same answer for that same example, but the key is what happens with if else then. Because now what I can do is that as I'm walking, I can push whatever the stack effects are of A and leave behind just the operations I need. And then when I encounter that if, I can transform it into a conditional, and I can store the entire state of the data stacks and return stacks, so that, and then push B and keep its effects around. And then when it's time to decode the else, I actually have the information I need to resolve the variables. And then the same thing with the other branch. And the only issue is that when I have to do a little bit of a fix up when I close off the then case, because I need to make sure that all of the variables that I'm going to reference at the end are declared at the beginning. This is just because this actually was something with JavaScript, you can declare things sort of as you encounter them with each branch, but with the GLSL shader, a variable has to be, if you're going to reference it at the end of the branch, it has to be declared before either of the two branches. So I have to bring those back up in front. And yeah, so possibilities is that this same basic approach would potentially allow me to support loops. It would be a little bit more involved. I would need to do something to standardize sort of the register structure that I squirrel away, or the variable structure I squirrel away, so that later when I'm going to branch back, I would be able to know that there's a variable for every value that's unique. Where currently with the conditionals, I'm able to get away with the possibility that there are values on the data stack that are duplicates that I will not, that I never assign a unique variable to. Whereas if I was doing loops, I would have to at every point that I branch in, give them unique variables, unless I do some very clever things. And it might allow me to more gracefully support function calls, which in principle, could be very fast in the WebGL shaders. Having recently actually played around with JavaScript engines, I'm a little, and their internals, I'm a little less convinced that I would get happy behavior with JavaScript engines. No, this is almost the last slide. Yes. And one fun thing is that I'm sort of intrigued by the simplicity of this approach. Is actually not very much code. And so I've been tempted to apply this context other than Haiku Forth for register allocation, because you can use the same approach, except that when you get to the point where you've run out of, have an infinite number of temporaries, because with JavaScript and with WebGL, because I'm relying on the underlying high-level compiler I'm sitting on top of. But if I had to allocate my own fixed set of registers, I could do this simply by kicking things off of it's basically spilling at the point that I run out of temporaries. And what's nice about that is that the data stack and return stack would act as a sort of a priority order for which registers to keep around, which might be fun. So that's all I have. Thank you. Questions? Bye.
A thought that I had as you were talking about adding loops
Yes.
is you don't have state variables right now,
Mm-hmm.
but you are running a loop.
Mm-hmm.
So a loop within a loop
Mm-hmm.
is really just the first loop with variables that have state.
Mm-hmm.
So why not go there first? Get some state
Mm-hmm.
into your, so that
You mean state between invocation?
iterations.
Huh? That's yeah. That's a good point. You mean variables in the sense of Forth variables? Yeah. No. That's good.
State variable.
Yeah.
Something
Yes, something that persists between. So one issue with that, actually, which is actually trickier, is that for the GL shaders, there aren't. There isn't. The assumption is that they're massively parallel, right? So you don't get the opportunity to have. You can have shared constants that you feed into them, but you don't have at least. Well, that's actually.
You don't have instance-specific values.
You have instance-specific values. The issue is that there's no communication between the.
Right.
That's yeah.
And that's all a loop is doing.
Yeah.
Is giving you communication. And it's going to delay, a loop will delay you
Mm-hmm.
and make the whole thing go slower, which is not purpose.
Yeah.
I don't see the point of having a loop inside these words, which are being executed, for every pixel.
Yeah, no, it's a fair point. I'm not sure that it's there are a few. So take for instance the fellow who was complaining about the Mandelbrot. It's on the one hand he's having to do repeat the letter several times for however many iterations. But the trouble is, even if I gave him loops, I can't really let him have any more iterations than he, so at best I could give him a more compact representation, but I'm not going to be able to actually help him run any faster. In fact, as you say, it will almost certainly be slower.
It will be slow. And that's the wrong purpose.
Yeah.
But a state
could be interesting, but state is tricky because of the confines in which I'm running. Yes.
And state, for every x, y, t value, you're at a point, and you want to save the x, y state, but the t state,
T doesn't.
Yeah. Now, what I could do conceivably is have some upfront computation that occurs, and then that's distributed to everyone. That would be feasible, right? That would let you do some interesting things. That's good. Mm-hmm. Yeah, no, in some sense that would be sufficient, right? But right now, a lot of people are, they define a word and then x, or right. To type it, yeah. No, that's a fair point. That would be more than enough. Yes, Gavin.
I'd like to issue a challenge to the community to produce the flag of Nepal.
You're trolling.
Cruel and unusual punishment.
Huh. Oh my.
Nepal. Would you repeat it?
Yeah, Kevin would like to issue a challenge to the broader Forth Haiku community.
He doesn't want to say it. I'd like you to all try the flag of Nepal.
I
Low hanging fruit. Yeah, I was about to do that, and then it went to.
Halfway up and delete the tower is the low hanging.
There we go. No problem at all, I'm sure. I mean, in some ways, this bit wouldn't be too bad. That it's not inconceivable. It's just a little bit tricky. Simple geometry.
You can't do it. A motion to adjourn is always in order. It's not debated. It takes precedence.
Oh my goodness, look at the time.
All right, we're going to lunch, everyone.